everyone, welcome back to the lecture video series of a medium transmission line and then the long transmission line, and precisely it is a performance analysis of the transmission lines. In the previous videos we discussed about the short transmission line, we discussed about the medium transmission line performance analysis by using several methods. We all understood that performance analysis of the medium transmission line could be done with the help of three different methods. That is, the first one is the end condenser method, and the second one is the nominal T method, and then the third one is the nominal pi method. Basically, we understood that the performance analysis is nothing but analyzing a transmission line with respect to the efficiency of transmission and as well as the percentage regulation, voltage regulation that a transmission line should possess. So using these three methods, we understood that it is possible to consider the effect of the capacitance along the transmission lines when the transmission line length exceeds 50 kilometers and 80 kilometers precisely. So from the point of view of the capacitance, line capacitance, in the medium transmission line itself, we have considered that the capacitance is not lumped, but it is distributed throughout the line. There's another way of analyzing the transmission line, that is the generalized constants of the transmission line. We always consider that the transmission line network as a two-port network. Here I have shown a two-port network, and in this V1, I1 are the sending end voltage and then the current, and in the port 2, V2 and I2 are the voltage and then the current at the receiving end. So we can say that V1 is the voltage at the input side, and 1 and 1 dash are the input terminals, and 2 and 2 dash are the output terminals or another terminals at the output side. So V2 is considered as the voltage at the output side, and then the I2 is considered as the current from the output side. Here the transmission system can be assumed to possess four terminal network, and it consists of two input terminals and two output terminals. So we can have the if at all we go with the equalized or equivalent diagram, the analysis would be too tedious. So here, if we can consider the two generalized constants, then it would be easy to express the output parameters in terms of input parameters. So here basically we are going to consider the four terminal network with the two input terminals, whereas where the power enters from into the network, and two output terminals where the power leaves the network. So according to this, we can consider that the Vs is the sending end voltage, Is is the sending end current, Vr is the receiving end voltage, and Ir is the receiving end current. Let the sending end voltage and then the sending end current may be expressed in terms of receiving end voltage and then the receiving end current through a set of parameters known as transmission line parameters or generalized constants, or it is popularly called as ABCD parameters. We will understand that why we need to have this ABCD parameters and how it is evolved from the binomial equations or the polynomial equations, and why it is to be used in the electrical network. So we can express the input parameters in terms of output parameters. Thus we can write this as Vs is equal to A into Vr plus B into IR, Is is equal to C into Vr plus D into IR. Vs and Is are the input terminals, input terminal parameters, that is sending end voltage and then the sending end current, and whereas Vr and IR are the receiving end voltage and then the receiving end current. So we can express with the help of A, B, C, D parameters that is used in this particular equation. So the network between the transmission line should be linear, passive, and then the bilateral. Linear network means it consists of the linear parameters. Passive network where it does not generate any power, and we are going to consider it as the four terminal network, and bilateral because it is considering both the input terminals as well as the output terminals. So the parameters A, B, C, D, which are generally complex numbers, that's why we denote it as A vector, B vector, C vector, and the D vector, and these are the constants which are known as the generalized circuit constants. Very, very helpful in terms of long transmission line, short transmission line analysis, as well as the medium transmission line analysis. We are going to see that how exactly nominal T method or nominal pi method can be expressed in terms of the generalized constants, as well as we will get to see that how the long transmission line can be analyzed with the help of ABCD. So A vector, B vector, C vector and D vectors are expressed, and these are all the complex numbers, and these are the constants which are known as the generalized circuit constants, and these parameters can be written with respect to the sending end voltage, receiving end voltage, sending end current, and then the receiving end current. Let A vector is nothing but equal to the ratio of Vs to Vr, where the current IR is found to be is at 0. B vector, that is equal to the ratio of Vs and IR, where Vr is set at 0. Vr is assumed to be at 0. And C vector is nothing but equal to the ratio of sending end current Is to the receiving end voltage Vr, where the IR is assumed to be at 0. And D vector is nothing but the ratio of Is to IR, where the Vr is assumed to be 0. Now here we can see that the parameter A and then the parameter D are dimensionless, because they are simply the ratio of the same dimensions, that is the sending end voltage to the sending end receiving end voltage, and then the sending end current to the receiving end current. So these two, A and D, are dimensionless, whereas B and C are having the dimensions. That is, C can be expressed in terms of B can be expressed in terms of Vs to IR, that is in terms of ohm, whereas C can be expressed in terms of mho, that is the ratio of the current to the voltage. Now, if the network is symmetrical, then parameter A is equal to parameter D. If the network is not symmetrical, or if it is reciprocal, then we can say that A into D minus B into C is equal to 1. So popularly, if the network is reciprocal, then we will write it as A vector into D vector minus B vector into C vector is equal to 1. If the network is symmetrical, then A vector is equal to D vector. Let's analyze this four terminal network in depth with respect to the symmetrical conditions as well as the reciprocal conditions. Let's take the first case of condition of symmetry for transmission parameters, and we can write the four terminal network with respect to this, where we are going to, in the figure A, we have assumed that the voltage is connected to the sending end, that is, let it be V1. Current from the sending end is I1, whereas the network is open at the receiving end, so only the voltage exists and the current is I2 is equal to 0. Figure B shows that there is no sending end voltage, that the V1 is equal to 0 and then the I1 is equal to 0, whereas the voltage is connected at the receiving end, that is V2 is connected, and then there is a current that is flowing into the network from the receiving end, that is I2. So here V2 is equal to Vs, that is V2 is equal to Vs here, whereas V1 is equal to Vs here, that is the V1 is the sending end voltage here, whereas here it is V2 is the sending end voltage. Now let us see that how exactly the symmetrical condition exists for a four terminal network. Let us from the figure A and from the figure B, let's consider the basic equation for the transmission parameters that can be written in terms of terminal parameters. V1 is equal to A into V2 plus B into minus I2, because the current is assumed to be flowing into the network because it is open circuited. Let us keep this as equation 1. I1 is equal to C into V2 plus D into minus I2, because the current entering into the network. Let's keep this as equation 2. Consider figure A, where from the figure A, V1 is equal to Vs and I2 is equal to 0, because at the output it is open circuited. So from the equation 1, if we apply this to the equation 1, V1 is equal to Vs and I2 is equal to 0, B into 0, and this is Vs will be equal to V1 is equal to Vs, so Vs will be equal to A into V2. Let's keep this as equation 3. Equation 2 can be written as, now we can write this equation 2 with this assumption from the figure A. I1 is nothing but equal to C into V2, because I2 is 0. So equation 4 is nothing but I1 is equal to C into V2 from the equation 2. Now with this equation we can write V2 is equal to I1 divided by C, and Vs is equal to A into V2. So Vs is equal to A into V2 is nothing but equal to I1 divided by C. From this, V2 is equal to I1 divided by C. So if we apply it to equation 3, then we can write it as Vs is equal to A into I1 divided by C, can be written as A divided by C into I1. So Vs divided by So Vs divided by I1 is equal to A divided by C from this equation. So consider the figure B next. So after finding out the ratio of Vs to I1 is equal to A divided by C, from figure we can understand that the voltage source is connected at the end, so V2 is equal to Vs, and there is a current that is flowing from the voltage source. So Vs is equal to, from the equation from the figure 2, I1 is nothing but equal to C into V2. I1 is nothing but equal to C into V2, and keep this as equation 4. From this equation, V2 is equal to I1 divided by C. Now what is Vs? Vs is nothing but equal to A into V2. So A into V2 means A into I1 divided by C, A divided by C into I1. So from the figure 2, okay, we can write it as, from the figure A, we have written it as Vs divided by I1 is equal to A divided by C. So now we can see that from the figure B, V2 is equal to Vs and I1 is equal to 0. Equation 1 can be rewritten as, what is equation 1? Equation 1 is V1 is equal to A into V2 plus B into minus I2. In this condition, V2 is equal to Vs plus I1 is equal to 0. So V2 is equal to Vs. So this can be written as, equation 1 can be written as V1 is equal to A into Vs plus B into minus I2. Keep this as equation 6. Now equation 2, from the equation 2 can be rewritten as, since the condition says that V1 is equal to 0, 0 is equal to C into Vs plus D into minus V2. Now C into Vs is equal to D into I2. Vs divided by I2 is equal to D divided by C. Keep this as equation 7. Now we have found out all the 4 parameters, that is the ratios. For condition of symmetry, A should be equal to D. So what is A? A is nothing but the ratio of the voltages. D is nothing but the ratio of the currents. So Vs divided by I1 is equal to Vs divided by I2. Vs divided by I1 is nothing but, from this equation we have found that Vs divided by I1 is equal to A divided by C. Whereas Vs divided by I2 is found out to be D divided by C. So A is equal to D. So for the condition for the symmetry of the 4 terminal network is proved. So A is equal to D. Let's consider the second condition, that is condition of reciprocity for ABCD parameters. To get the reciprocal condition, AD minus BC should be equal to 1. Let's consider two diagrams written here, figure 2A and 2B. In the figure 2A, the voltage source is connected at the V1. So V1 is equal to Vs and I1 current is flowing into the network. I2 at the output it is short circuited, so the current I2 is flowing. So let's consider the current through the source as I2 dash. I2 dash is nothing but equal to minus I2 because it is a current source. So I2 dash is equal to minus I2. Now V2 will be equal to 0 because it is short circuited. So here, considering the equation for the basic equation for the ABCD parameters, V1 is equal to A into V2 plus B into minus I2. Keep this as equation 8. And I1 is nothing but equal to C into V2 plus D into minus I2. That is equation 9. So consider the figure 2A. In the figure 2A, we know that V1 is equal to Vs, V2 is equal to 0, I2 dash is equal to plus I2, because here it is considered. So in the figure. So now we are going to consider it as Vs is equal to B into plus B into I2 dash, and equation 8 can be rewritten as Vs is equal to V1 is equal to Vs and V2 is equal to 0. So Vs is equal to plus of B into I2 dash, because I2 is nothing but equal to I2 dash is equal to minus I2, whereas I2 is equal to plus of I2 dash. So B plus B into I2 dash. So where Vs divided by I2 dash is equal to B. So equation 10. Now consider the figure 2B. V2 is equal to Vs, V1 is equal to 0, I1 dash is equal to minus I1. I1 dash is equal to minus I1 and I1 dash is equal to minus I1. V2 is equal to Vs, V1 is equal to 0 because it is short circuited. Now keep those conditions in the equation 8, and equation 8 can be rewritten as 0 is equal to A into Vs minus B into I2, that is equation 11. So with this, equation 11 can be rewritten as AVS is equal to B into I2. AVS is equal to B into I2, whereas this can be written as minus of I1 dash, because I1 is nothing but equal to minus I1 dash is equal to C into Vs minus D into I2. Keep this as equation 12. Now So equation 12 is minus I1 dash is equal to CVS minus DI2 from the equation 11. So we have applied this condition of 2b, that is V2 is equal to Vs and V1 is equal to 0 and I1 dash is equal to minus of I1. So now minus of I1 dash is equal to C into Vs minus Di2. From the equation 11 we can also have minus AVS, as I already told you, like AVS minus AVS is equal to Bi2 minus Bi2. So minus AVS is equal to minus Bi2, minus gets cancelled on both the sides, AVS is equal to Bi2. I2 is nothing but equal to A divided by B into Vs, that is 30, equation number 30. Now I2 is also known, so on the output terminal I2 is also known, A divided by B into Vs. Now substitute equation 13 I2 value in equation 12. Now I2 value means minus I1 dash is equal to C into Vs minus D into I2 is A divided by B into Vs. Now simplify this equation, minus I1 dash is equal to B into C, cross multiply, minus AD divided by B into Vs. Simplify this equation further, Vs divided by I1 dash is equal to B divided by AD minus Vc. Network is said to be reciprocal if Vs divided by I1 dash is equal to Vs divided by I2 dash. That is B divided by Vs divided by I1 dash is nothing but B divided by AD minus BC is equal to, from the equation earlier we have found out that Vs divided by I2 dash is equal to B. So AD minus B, if we take it common, B into 1 over AD minus BC is equal to 1. So AD minus BC is equal to 1. Now the condition for the reciprocity of the network is AD minus BC divided is equal to 1, whereas condition for the symmetry is A is equal to D. So we have proved two conditions for the 4-terminal network. One is the symmetrical condition and the other one is the reciprocity condition. Let us apply this ABCD parameters analysis to the different type of transmission line, like short transmission line and the medium transmission line, as well as to the long transmission line. Let's first consider the short transmission line here. We all know that in the short transmission line, since the length of the transmission line is found to be less, we are going to consider only the resistance and then the inductance as in series, and we are going to omit or we are going to neglect the effect of the capacitance, and we are going to write the network as the Z in series, that is the supply network in series with the impedance, and then there is a receiving load, that is the load is connected at the end. VR is the voltage applied, or VR is the receiving end voltage, R is the resistance of the network, XL is the inductive reactance, put together constitute the impedance of the circuit, IS is the sending end current, and then the VS is the sending end voltage. After writing this equivalent diagram of the short transmission line, let's understand effect of the line capacitance is ignored, and for the analysis we are going to consider the three-phase system as a single phase system. So we have considered only one neutral and then one line single phase system. We have IS is equal to IR, IS is equal to IR, that is vectorially, and VS is equal to VR plus IR into Z. VS is equal to VR plus IR into VS is equal to VR plus IR into Z. That is the impedance of the line. So keep this as equation 2. Now the defining equations for the transmission line parameters are nothing but VS is equal to A into VR plus B into IR, IS is equal to C into VR plus D into IR, all vectorials. Now comparing equation 1 and 2, which are the set of equations for the sending end current and then the sending end voltage, with the ABC defining equations, that is the set of equations, then the standard equations, we can write this by comparing this. A is equal to 1, Vs is equal to A into VR plus B into IR. Compare this with the equation 1, then we get only A is equal to 1 because there is no factor for the Vs is equal to VR into IR plus Z. So now if we compare this, A is equal to 1 because there is no cofactor for the VR here, and B into IR is compared to the IR into Z. So B is nothing but Z. So B vector is equal to Z vector. Compare this IS equation with the IS equation. So C is equal to 0 because there is nothing for the C here, and C into VR, so there is no associated factor here, so C is equal to 0.